Coulomb in the 1770s explored how much force is required to pull a body riding on a surface, motivating friction, where this is the M force and the T force. And so he concluded that T is equal to a friction coefficient times the normal force. If we divide both forces by the apparent area of contact, then we could rewrite this by saying that tau is equal to sigma, and instead of putting a coefficient, we can put the slope of an angle. And this is Coulomb condition at failure. So this is the ultimate shear stress that can be resisted. And because the water doesn't resist shear, whenever we talk about shear strength, it's going to be the effective normal stress on that plane. On the other hand, Coulomb was looking at the state of stress at a point, and what happens if, instead of looking at the full point, we cut it in an angle and we see what are the stresses that are required to maintain it in equilibrium, to take that free body and maintain it in equilibrium. And so for the point under equilibrium conditions, he showed us that we could plot the state of stress as a circle in the tau sigma space. Now, as you can see, both of them are talking about the tau sigma space. So even though they did not coexist, this is 18th century, Mohr is in the 19th century, actually they do coexist in the tau sigma space, where this is Coulomb, the straight line, where tau at failure is equal to sigma effective tangent phi, and this is state of stress at a point in equilibrium according to Mohr. The question is, what happens when the state of stress keeps expanding and all of a sudden it reaches the failure condition, it touches the failure envelope. And when that happens, in some direction, the state of stress at the point in equilibrium has reached failure conditions. And now we have several questions to ask. What is the maximum stress that we can apply until the system reaches failure? Or what is the ratio between the sigma maximum and the sigma minimum? And what is the direction at which failure is going to be encountered? Because it's going to, that state of stress will exist on some angle theta. So let's address the first question. What is the maximum stress anisotropy that a soil may experience? And so this is the question. What is sigma 1 over sigma 3 maximum for a granular material where the behavior is frictional? And so what we are asking is, how much is this quantity, sigma 1, compared to this quantity, sigma 3, when the circle is at failure? Now, as you can see, sigma 1 is the center plus a radius, while sigma 3 is the center minus the radius. Therefore, we are going to call this quantity the center, the location of the center, and the radius is the one that connects to the point. So sigma 1 is the center plus the radius, where sigma 3 is the center minus the radius. Let's redraw this for clarity. And this is the circle at the verge of failing, touching the failure envelope. This is the radius, and this is the distance to the center. If you look at this triangle, the radius is the opposite to the angle, and this is the hypotenuse. Therefore, r over c is equal to the sine of phi. So if we divide numerator and denominator by c, I get 1 plus r over c over 1 minus R over C, and this is the maximum stress anisotropy the soil may experience is 1 plus sine phi over 1 minus sine phi. You may have seen this also when we talk about retaining walls, whether we push them or where we release them. The maximum force that we can put for the system to passively resist is this stress anisotropy. We call it K passive. But really, the important thing I want to highlight here is that a soil, for being a granular material, cannot take infinite stress like this pencil. I can push this pen with very high force with zero lateral confinement, so it has infinite stress anisotropy. I cannot do that with the soil. A soil reaches a maximum stress anisotropy, which is totally determined by its frictional strength. For example, if phi is equal to 30 degrees, this is 1.5 divided 0.5, this maximum stress anisotropy is 3. And it rarely exceeds 4 or 5. That's it. We cannot mobilize more stress anisotropy in a granular material where the strength is controlled by frictional shear resistance. We said that when the circle is touching the failure envelope, the relationship between sigma 1 and sigma 3 is totally determined by the friction angle by 1 plus sine phi over 1 minus sine phi. By the way, that has a trigonometric identity, which is tangent square of 45 plus phi over 2. But you may also wonder, what is the orientation of the stresses when at the point of failure? This is the question. We have sigma 1 applied here, while we have sigma 3 in the horizontal direction in a typical axial compression triaxial test. And the question is, when it reaches failure, we know that it's touching the failure envelope here, and now what is the direction where those stresses are found in this specimen? And so we are going to use Mohr circle. We need to identify the origin of planes. This is the point that represents phase A. This is the point that represents phase B. Therefore, we're going to draw a line parallel to phase A, and where it intersects the circle, this is the origin of planes. Let's confirm. Let's draw through point B a line parallel to phase B, and indeed it touches the circle here, so this is the origin of planes. From the origin of planes, we connect to the point where the stresses are at failure, and this is the orientation, theta, of the failure plane. And clearly there must be a relationship with the friction angle. Let's see if we can identify it. And so let's recognize the following. Because this is a tangent, the normal, this forms a 90-degree angle. And because of one of the properties of a circle is that this angle is twice as this other angle that you see here. So let's write this down. If this is the friction angle and this is a 90 degrees, so this is 90 minus phi. Therefore, this is half. This will be 45 minus phi over 2. Now, there is another property of circles that whenever a line connects two extreme points, the other two lines are going to form a normal intersect. So this is normal. So now this must be the complement of that. Therefore, the angle of the failure plane is going to be the complement, which is 45 plus phi over 2. So this is a fairly steep angle here at 45 plus phi over 2. The video on Mohr circles told us that the apex is all we need to know to define Mohr circle. Because out of the 3 points, we know the x and y position, and we know that the apex of the Mohr circle is always resting directly on top of the center, which rests on the tau equals 0 axis, in other words, on the sigma axis. Therefore, if we know the apex, we just draw a vertical line to the sigma axis, and we can draw with the compass, we can draw the circle. This is very valuable because we don't need to draw circles anymore. However, if we are only going to follow apices, we don't know when the circle reaches the failure envelope, because the apex is not touching the failure envelope. So if we are going to work only with the apices, that means that we're going to be in the QP, which is totally coexisting with sigma tau. If we use this definition of QP, then we need to define this other line that actually goes through the apex, so we'll know when the circle has reached the failure envelope. So if this has an angle phi, let's call this angle alpha, and we would like to know the relationship between those two. So let's focus first on, this is the radius, let's call this the center to the circle, and now we have this normal to the failure envelope, which is also a radius. So if you look at the triangle defined by the failure envelope phi, this segment, this radius, is the opposite of the friction angle at the acute angle here. So R over C, from the point of view of in the tau sigma space where the failure line is equal to the sine phi, while R over C from the point of view of the QP space where we are only looking at the apex is equal to the tangent of the alpha angle. Therefore, we see right away a relationship between alpha and phi, so we can work only with the apices. Now we are ready to do some stress paths. We're going to consider the following situation. We are in the subsurface. We are starting from a condition of K0 state. So sigma z is greater than the sigma horizontal if it is virgin loading. And this is sigma z, and this is sigma horizontal smaller than sigma z. So in a Mohr circle tau sigma space, this situation is as follows. I have sigma z, and this is sigma x, K0 of sigma z. So this is a circle. We're going to start on this apex. So remember, we can always put here Q and P, and we can go from one to the other without delay because we just go down and we draw the circle. So let's start from that situation, and we're going to show only the QP in this case to make the story simple. This is our initial condition. Now we could have a situation where we begin pushing horizontally because there is a bulldozer that is plowing into it, there is tectonic motion, and so if we push horizontally, then the horizontal stress begins to increase. So look what happens to the Mohr circle. Of course, you still have the vertical, but the horizontal stress increases faster, and so the Mohr circle means that the sigma horizontal, this is the sigma horizontal was here, now begins to move in this direction, sigma horizontal, and as you can see, the apex goes down. So this is, once again, in a tau sigma space. Let's capture it in the Q space. And because we are following the apex, you can convince yourself that this is going at a 45-degree angle. And so this is this path where we are subjecting the system to lateral compression. Let's take another case in which we actually do the opposite. For that element, what we are going to do is we're going to relax some of the horizontal stresses and allow it to relax laterally. That means that the horizontal stress is going to decrease from the initial condition, and the Mohr circle is going to increase. Therefore, the apex moves in that direction, and that is for lateral relaxation. So that will be a lateral extension case. For example, we were doing an excavation and removing material out of it. Of course, we can always add a vertical load, and if we add vertical load and maintain the horizontal constant, Mohr circle is going to, from the initial condition, the vertical is going to increase, and so Mohr circle will increase in this direction, and the apex will follow a 45-degree up, and this is axial compression. While, lastly, is if you take the element and you actually unload part of the vertical load, you remove part of it, maintaining the horizontal constant, then the circle will be from the initial situation, the vertical stress is going to decrease and the circle is going to decrease, and this is the stress path. So in this case, we are doing an axial extension. Let's infer how are these elements going to evolve. This first case was lateral compression, and the element is going to get thinner and taller. This case is lateral extension is going to get shorter and wider. Lateral extension. This is for axial compression. The element is going to get shorter and wider. Finally, for axial extension, is going to get thinner and taller. As you can see, the lateral compression and axial extension, lateral compression and axial extension, the element is getting taller and thinner. And lateral extension and axial compression, the system is getting shorter and fatter. These are the four classical stress paths, and they evolve differently in the tau sigma QP space, but it is important to realize that the deformations are also going to be quite different, from getting taller and thinner or shorter and fatter in the different regimes under those stress conditions without additional boundary controls. Of course, this is going to be limited by the limiting anisotropy. So these paths are going to encounter what now we call the alpha plane. Remember, tangent alpha is equal to sine phi, and they're going to encounter this failure plane in the upper part or in the lower part. So that is the limiting equilibrium condition. When we look at the coupled behavior between pore fluid generation and deformation, we're going to see that these stress paths apply only for drain conditions, and the story becomes more complex under undrained conditions.